Welcome back, everyone. In this video, we'll resume topic number one with focus on loading and analysis. So, this is a part where you will understand how to distribute the dead load and live load from the structure into structure elements such as beams and columns. First, we need to fresh your mind that type of loading, either dead loads, which is permanent load, include the own weight of the structural elements, and superimposed dead loads, which is any load that you cannot move frequently and it's permanent on a structure, such as floor finishes, wall, ceiling, HVAC systems, and cladding. Live load is any load that either in change frequency or amplitude. And with focus on roof live load and live load, we will also discuss what so-called reduction factors for live loads. You can check IPC table 1607.1 for live load values, or ASCE table 4.1 for the same values, and as other sections like 4.7, 4.8 for ASCE 7-16 for the reduction factors. Here, as you can see in this slide, I'm putting snapping shots from some tables. So first table is from ACCI 7, where you can find directly, based on your functionality of your building, the value of your live load as a uniform load per pound per square foot. For example, if you have office building, the offices are around 50 pounds per square foot. If you are apartment building, the private rooms around 40 and the public rooms around 100. Schools, based on the functionality of each area, classrooms, corridor, first floor corridors, and even storage warehouses, either light or heavy, and stores. So this give you what's so-called, we say, L node, which is a load unreduced load, original load before we reduce it. We also have some provision from IBC 1607.10.1.2 that heavy loads that exceed 100 psf shall not be reduced. And partition load, if you read this clause, you'll see in office building and other building with partitions subject to change, for partition which shall be made, whether or not partition are shown on the construction document, unless specified live load is 80 psf, the partition live load shall not be less than 15 psf. So if your live load is less than 80 psf, you have to consider partition of at least 15 psf. And this one shall not be reduced. And if you're under 80, you are allowed to reduce. Since you are exceeding, actually, you are below 100, which is the threshold for not reducing the load. The reduction factor here, as you can see, if the member, you can reduce the live load if the member's support area of KLL AT more than 400 feet square. KLL, what's so-called live load element factor, is function of if you have interior column, if you have exterior column without cantilever, edge column, corner columns, edge beam without cantilever, interior beams, and all others. In this equation, you can see that L naught is the original one that we got from the table from previous slide, and L is a reduced one, and the factor is 0.25 plus 15 square root KLL AT. KLL, you can get it directly from this table, 4.7. AT is the tripotary area. And you can calculate it from this slide. If you can see the column here in the middle, the tripotary area is this area, almost the average of each span in each direction. However, what's so-called influence area is the area that where any load will influence the column. So very important that you know that this is actually the factor reduction, and this is the original load from the table. All you need to know is to get KLL from table 4.7 and calculate AT to get your reduction factor. So a member supporting large tripotary area is less likely to be loaded all the time. That's why we are allowed to reduce it. If KLL is times AT is more than 400, you are allowed to reduce. So the reduction factor will be 0.25 plus 15 divided by square root of KLL AT. If your member is supporting one floor only, which is more likely to be a beam, you cannot reduce more than 50%. If supporting two floors, you cannot reduce more than 60%. As we mentioned, AT is a tripotary area, KLL is a live load element factor. This is all we discussed was for typical floor. Remember, if you have a storage that exceed 100 PSF, you don't reduce. Miscellaneous loads that carry may occur on building roof, so that's why you have to include at least L naught of 20 PSF, but this should always be more than 12 PSF. Your reduction factor will be function of tripotary area AT and the slope F, which is the number of inches per rise per foot length. So if you have a slope 1 to 4, let's say 1 to 4 is equal to 3 to 12 inches. So your F value will be 3 inches for a rise of 1 foot. So R1 will be 1 if your tripotary area is less than 200. If your tripotary area between 200 and 600, your R1 factor is 1.24 minus 0.001 AT. If you are more than 600, you are 0.6. R2 is function, as I mentioned, of the F value, which is number of inches per rise per foot of slope. As you know, as your slope increases, probability of having live load decreases. That's why if you are less than 4, you basically have 1. You are between 4 and 12, you have to use 1.2 minus 0.05 F. If you're more than 12, which is slope 1 to 1, your reduction is 0.6. And you multiply R1, R2 times L naught, which is most likely to be 20 PSF, and LR has to be calculated and not less than 12 PSF. Let's go through an example to illustrate that. The beam plan that we're going to show in a few slides has a beam of 12 wide, 2.5 deep. So your beam is with this dimension. Your slab is joist, and the weight is 84 PSF. The floor is ordinary flat floor. The slope is half in 12 inches. So if you have half in 12 inches, mean that your F value is half. It's a not used for public assembly. Floor number 5 is light storage of 125 PSF. All floor are office occupancy. Assume 10 PSF superimposed dead load. Normal weight concrete is 150 PSF. Neglect lobbies and corridor. Roof loads are 20 PSF. Calculate dead load on column B1, live load on column B2, and dead load live load in the beam between on the center line of B between center lines 1 and 2. Let's see the plans. You have a plan view of the building. You have 4 span in X direction, 25 feet between A and B, 20 feet between B and C, 20 feet between C and D, and 25 feet between D and E. And you have 2 spans in Y direction, 2 feet between 1 and 2, 2 feet between 2 and 3. Your beams runs in the Y direction here, as you can see only. And your slab is given with the load 84 PSF. And the beams are, as you mentioned, 22 by 20.5 inches, and the typical column is 22 by 22 inches. And the elevation, you will have the roof here. You have story number 5, story number 4, story number 3, story number 2, story number 1, which should give you level or slab 1, slab 2, slab 3, slab 4, slab 5. As you can see here, 5 carries a roof. Storage is this floor, and the other are office, and we don't worry about this much because this is the first floor. And as you can see, if you focus on the dead load on this column and XB2, what we do is this column is actually carrying the slab first, and because the beam runs in this direction, the column tributary area will be the average of this distance, 2 spans here, and the average is the 2 spans here. And as you can see, the load on the column has to be in kips. So you have to multiply your load, which was given as 84 PSF, pound per square foot, by area, which is going to be the tributary area. Average is 25 and 22, divided by 2, times average 20 and 20 is 20, times 84 by divided by 1,000 to convert from pound to kips. So it will mean that the slab will transfer a load of 39.5 kips on the column at each floor, right? Column also carried the beams. You can see here this column carried the beams halfway from here, halfway from there. The average length here is now going to be 20 feet. And you need to remember the beam is made of concrete, and unit weight of concrete is 150 pound per cubic feet. So in order to get into kips, you have to multiply times volume. So that's why you have the length of 20 and the volume of the cross section of the beam, which is, if you review, it was 22 wide, 20.5 deep. Here we are getting the area of the cross section divided by 144, which is basically 12 by 12 to convert from inches to feet. And you multiply times 20, which is the length of the beam, and the unit weight of the concrete is 150, divided by 1,000 to convert from pounds to kips. You get 9.4 load of the beam at each floor. Also, the beam carries its own weight. In this example, we have typical columns of 10 feet, and the first floor is 12. That's why you have to do it twice. The column now is 22 by 22, as you can see in the typical 22 inches by 22 inches. And the own weight has to be the volume of the column, let's say this column, times the unit weight of concrete. Unit weight of concrete is 150 over 1,000. The volume is the area of the cross section, 22 by times 22 over 144, to convert from inch square to feet square, times the height of the column, which is 10, as you can see here. That gives you the weight of the column at this floor, this floor, this floor, and this floor, about 5 kips. The first floor or story, the column is 12 feet. So it's going to be the same equation, except that you're going to replace the typical height by 12 feet now, and you got 6.1 active here. The last one is a superimposed dead load that you will treat it as a unit of a slab, unit weight, as you did in the load of a slab. It's around 10 psf, so you have to multiply time area. This is going to be the tributary area, the average of the two distance. The first one is 25 by plus 22 over 2. The other distance average is 20. You multiply time 10 over 1,000 to convert from pound to kips. You got 4.7 kips applied as a superimposed dead load on the column for each floor. If you want to summarize in this slide, you will see that the joist of the slab actually is 39.5, and if I use the joist as red, you will see that you have red here, you have red in each floor. If I convert to blue for the beams, you're gonna get 9.4 kips. You also have beams in each floor level. And if you have the weight of the column as green, you will get the typical column acting as 4 column, column 1, column 2, column 3, 4 from the top. And rather than choosing this color, is the first story going to be here, and the superimposed dead load will be in every floor level. So now we're going to go to the live load, and please pay a very high attention with me. First, we're going to deal with the roof. The roof floor was given as 20 psf. Here are the guiding reduction factor. If you remember, the F was half inches. That's why R1 has to be 1 because you are lower than 4. The tributary area, as we calculated, was around 470, which is the 23.5 times 20. As you can see it here. That give you R1 between 200 and 600. So you have to use 1.2 minus 0.018 from this equation. This give you R1 and R2 as 0.073. You multiply now R1, R2, and L note, give you 15 psf, which is more than 12 psf. Now to calculate the load from the roof, you have to multiply that times the tributary area because we want it to be in kips. So it's 7.1. The level 5 with a storage of 125. So you should not be reduced based on 1607, 10, 1, 2 heavy loads. So the axial load is 125 over 1,000 times 470. I'm going to give you 58.8 caps applied. If this is your roof and this is your roof, this is your storage, and you have office floors, office, office, and office. You already reduced the roof, storage is not reduced. Now you have to deal with the offices. Okay, for the offices or typical floors, please note that it was given by the table. It should be 50 PSF. This is actually less than 80, so we have to include partition of 15. Also, it's less than 100, so we can reduce, right? You can read it here very clearly. Non-reducible of 15 PSF must be included as partition, and you have to reduce the 50 kips. Okay, so now let's go one by one. We know that we are dealing with interior column, so our KLL is 4. KLL is 4. However, in this reduction factor equation, as you can see, it's 50 pounds per square foot of office building L note, and 25 plus 15 over square root of KLL AT. KLL is 4. However, is AT different from for each column because you have the roof, as we mentioned, you have the office, the storage, and you have office and office and office. This column actually is carrying one reduced office, so the tributary area will be AT. This column is carrying two reduced office, so it's 2AT. And the last one is carrying three office reduced, so it's going to be 3AT. So if you want to make the general equation, 50 over 1,000 will be the load L note. The reduction factor is 0.125 plus 15 square root of 4, which is KLL. AT is the tributary area, which is different for each column based on how many reduced office floor you carry. And AT is the tributary area of the column to convert from PSF to pound or kips. Now we can go and apply. Before we apply this table, we have to know that there is non-reducible live load due to partitions, which is 15 over 1,000 times 470, gonna be 7.1. Let's start doing this table. You have to know that you have now 5 stories. This is story 1, story 2, story 3, story 4, story 5. So this is column for story 1. This is column for story 2. This is column story 3. And this is column story 4. And this is column story 5. If you review what we have done from the dead load, the dead load for on this column 5 will be 58.6, and for column 4, column 3, and column 2, except column 1 will be a little bit higher because the height is the only difference. It was higher by 2 feet. We know that we also have what we call non-reducible live load in this storage, right? As pardon me here, this was the storage, and this was office, office, and office, and this is the roof. In this column number 5, we actually reduced the roof load. That's why you have the reduced load here was calculated as 7.1. Nothing was non-reduced. You know that this is storage carried by story or column story 4, this column, and it was not reduced as 558.8 as storage, and all the other columns in story 3, 2, and 1 as non-reduced load of partitions here, here, and here, as you can see, 7.1, 7.1, 7.1. Here are the KLL AT. You know, KLL is 4. AT is based on where you are in the floor. If you are in column 3, you only carry 1. So your AT will be 1 AT, which is here. You can see it's 4 times AT, which is 1 AT 470. In this column, carry 2 reduced office, so it has to be KLL 4 times 2 times 470. And the last one is carrying 3 offices to be reduced, so KLL is 4 times 3 times AT is 470. If you go and calculate only reduction factor, you will see it 0.6, 0.5, 0.45. Now you can calculate based on the number for the reduced one, which is going to be this factor times 50 over 1,000 times the tributary area 470. That will give you a reduced load of 14.1, 11.8, and 10.6. If you add the reduced to non-reduced, you can get the loads, the live loads. And if you add dead load to live load, which is column 1, to this column number 1, 2, 3, 4, 5, 6, 7, this is 1 plus 7, give you the total dead plus live. But remember, this is not cumulative because this column is carrying all the columns and floors and beams above. So you have to actually keep this one. This value will be adding this to this one. This one will be carrying the 3 floors up. This one will be carrying 4 floors up, and this will carry all the floors because it's a first story column. You can repeat that for beam on line B between X1 and 2. This beam, let's start with the dead load. This beam actually, because the beam actually run between in the Y direction, this beam will carry half the load of the slab from the right, half to the left, and has to be line load now. So you have to convert the PSF, pound per square feet, to pound per pound or kip per foot. You have to multiply the value of 84. You have to divide it first by 1,000 to make it kip. And this number is the distance perpendicular to the beam, which is average of 25 and 22 with 23.5. It give you 20 kip per foot linear load on the beam based on due to the joist or the slab. The second one going to be the own weight of the beam. We also need it as linear kip per linear foot. So you will multiply the cross section of the beam, which is given before as 22 by 22.5. You multiply that by 150 unit weight of concrete. You also need to divide by 1,000 to convert to kips, and you divide by 1.44 to convert from inch to feet, inch square to feet square, and this will give you half kip per foot as a uniform load on the beam. A superimposed load will be very similar to the weight of the slab, except that you replace the weight of the slab by 10, which is the superimposed load. Now you can summarize that your weight of the slab or the joint will be 2, weight of the beam will be 0.5, superimposed will be 0.3. You add them up, you got 2.8 as total dead load. If you want to go to now to the beam where it is for live load, remember the beam on a typical floor, they ask for a typical floor or any floor will be as follows. They actually ask for typical floor So the beam KLL value was interior beams. The KLL value will be 2. Okay, and the beam tributary area carry half of the span here and half of this span will be 470. So the reduction factor that you can see here, you can just plug here 2, plug here 4.470. You will get a reduction factor. You have to multiply that time 50, which is a uniform load. And after that, you have to multiply time 23.5, which is what we said about the perpendicular distance. So we get the load in K per foot. Remember, this is a typical floor, and the load is 50. Load is 50. You have to include the partition, not reduce. It's going to be multiplied by the perpendicular distance of 23.5. So you got unreduced load of 0.4 and reduced load of 0.9. That's going to be total live load of 1.3. And the only thing left in this slide or this part of the presentation is how to include the live load factors. All we have dealt with is loading at this point. So the live load LRFD actually principles are that design strength has to be more than the required strength. So design strength would be reduced a little bit by phi factor. However, required strength would be equal to the loading that we need to design for. And you have different type of loads. You have snow S, rain R, live load L, roof load LR, wind, snow and earthquakes. You go to ACI table 531, you will have bunch of load combination from A to G. And you can see the first one, including the load, is 1.4. The second one is 1.2 plus 1.6. Live load, if you have floor, it will be 0.5 times L roof or snow or rain, etc. As you can see here. And you can see another load combination that include wind and earthquakes. For example, in this slide, we are showing that you have so many different dead load, live load roof, rain, and snow. However, you also have wind load that can apply in two direction. What you need to do here in this frame is to draw the typical moment diagram for the vertical loads, or the load applied vertically, which is the gravity load, dead loads. The moment will be always look like that if you draw in the tension side. So the mid span will always be positive numbers, and the support will be negative moments. And this will apply to dead load, live load, rain, and snow. And you can see here in this table, the support is negative values and midspan positive values, and the shear also provided. Under wind load, if the wind is blowing from left to right, your moment will have diagram will be this if you draw from tension side, and if you blow from the different direction right here, it will be similar, the opposite. So you'll always have in midspan almost zero value, and at this section it can be positive and it can be negative, so it's plus or minus. So all you need to do is to see which load combination will be applicable. Applicable load combination, as you can see here, you have 1.4 dead loads because you have dead loads. You have 1.2 live load. You don't have live loads, so you can cancel live loads. And have 0.5 either LR, you have LR, S, or R. So what I would tell you to do that looks like R R is higher than LR and S, so most likely going to be R to be used. In this equation, also going to be R used. You can cancel LR and S, but now you have 1 live load, you have live load roof, and here is a wind. So you're going to use wind. And here you will keep dead load, wind. You don't have live load, and you can also use only R because it's higher. And in this equation, you have earthquake, so and snow. So earthquake is 0, live load is 0. You can have this for snow load, and this is for wind, and this is you don't have earthquakes. So if you want to go equation by equation, the first one will be the first equation A, 1.4 dead load. You can calculate at the support and at the midspan and for shear. In the second equation, which is B, it will be 1.2 dead load plus 0.5 R, as we discussed in the previous slides. And here is at support and midspan and shear. And this equation, which is 1.2 plus 1.6 LR or S or R, is going to be R because higher R, and you have 0.5 wind. But remember, wind at sub midspan is almost going to be 0, so you don't have the third part. But at the support, it will be plus or minus, so you have to try the plus or minus here to and get the maximum. And you also you can try the negative, as I mentioned, and here is going to be the different value at the support, and the midspan is always wind 0. And you can repeat that again for the equation D and equation F. And you can come up with which one is more critical for a support, which one is more critical for moment in midspan and the shears.